Very good morning, students. Welcome to the new semester, that is 4-1, and in this semester we are going to discuss the subject radar systems. So here, what is the meaning of radar? Radar in sense radio detection and ranging. That means here we are transmitting a radio signal through the transmitter, and the antenna is going to transmit that signal to a distance, to a particular direction, or to a distance in a particular direction, and the receiver that detects the echo signal from the reflection of the object. That means whenever we are transmitting a signal, it will be received, or it will be hit by a target, and the received echo signal will be received by the receiver. By the receiving section, we are going to identify that there is a target. Radar is an object detection electronic device that uses ultra high frequency or a microwave part of the radio frequency spectrum to determine the position or range of the object. So here now we are using this radar. Radar means, as we have already told, that radio detection and ranging. That means we are detecting whether there exists a target, and also we are also finding the range of the target. So this works with we are transmitting the signals. Those signals are electromagnetic signals, that is electromagnetic waves, and the frequency of those waves lies between 30 Hz to 300 GHz. That means we are transmitting whatever the signal we are transmitting, it should be within the range of 30 Hz to 300 GHz, and they are generated by electronic devices called as a transmitter. So these signals, or these wave frequency signals, are generated by a transmitter which is connected to an antenna, and by the use of this antenna we are going to radiate those signals or those waves by a radio receiver connected to the another antenna. That means whenever we are transmitting the signal, the other end should be containing of an antenna which is at the receiver section, and that receiver antenna will receive the signals whatever we are transmitting. And these are widely used in modern technology in radio communication, radar navigation, and remote control and remote sensing. See, these are having a wide range of applications. These are used previously. So nowadays also we are using these radar in order to find out the movement of the target. That means, for example, whenever a rocket is launched, we are finding the position of that rocket through these radar signals only. See here, see in this picture, a radar antenna is transmitting a signal, and that this signal is hit by any target, and it is going to reflect back to the radar station. So by this operation, we are going to find that there is an object, and we are also finding the range of that object. So see here, radar sends an electromagnetic pulse transmitted through the atmosphere. So objects that are called as targets in the path of pulse will scatter most of the energy, but some will be reflected back to the radar. That means whenever we are sending it signal, it will be transmitted through the atmospheric medium. So most of them, objects in which the path called targets targets in the path of pulse will scatter most and the energy, but some will be reflected back to the radar. That means we are sending a beam of signals. Some of the signals will be hit to the target, and the reflected signals will be written back to the radar stations. So the signals which are written back to the radar stations, based on those signals we are going to find the range of that particular target. See, secondly, the scattered radiation will go to the receiver. If there are more targets, then the scattered signal combine to form a stronger signal. Then the value of range, position, direction and altitude is measured by these scattered signals. As I have already told you that by the usage of that scattered signal, we are going to find out the range and what is the position of the signal and in which direction it is moving, and also we can also find out the altitude and longitude of that particular signal. So usage of radar, where we are going to use these radar signals in our modern or in our daily life. See, in military applications to determine the target positions, that means in order to identify the missile detections, so we are using this one. In aviation, that means in aircrafts which is going to warn about the obstacles in their path, that means the pilot who is in the cockpit will receive the signals or will receive some commands from the ATC. ATC is nothing but air traffic control. That means whenever there is an obstacle, the ATC will going to give some ATC will going to give some instructions that there is some obstacle, so you just reduce your speed or reduce your altitude or increase your altitude, like that. So secondly, third one, marine radars to prevent collisions from other ships. Marine radars, the ships which are moving below the water. So in order to avoid the collisions between two ships, we are going to use this type of radars. And for the next one is meteorologists and weather forecasting to determine the weather. As we have already seen that in weather report they are going to say that weather forecasting. So by using these radars, we are going to find out the weather forecasting also. Geologists to determine the composition of Earth's crust. So what type of material is present within the Earth's surface? These type of things will be identified by using these radars, and it is also used by the cops to determine the vehicle speed. Suppose nowadays we have a limited speed to the vehicles. Whenever we are crossing the limit of the speed, or whenever we are breaking the traffic signals, then there will be a challan for us. So here at that particular moment we are going to use this type of radars. So what are the advantages of radars? So whenever, see, first one, radar can operate in darkness, haze, fog, rain and storm. Suppose if you are using a mobile phone, if the signals are if it is raining very heavily, then sometimes we are going to lose our signal. But by using these radars, we are not at all going to lose any signals. So that means these radar works in darkness also, fog also, rain and snow. Okay, and the next one is radar can be determined the position, range, angle and velocity of that object. That means here we are also finding the range, which cannot be done by the other systems, and velocity, angle, altitude, everything. That means we are tracking it by step-by-step process. And some of the limitations are radar cannot resolve in details like the human eye, especially at a short distance. That means whenever the radar is not going to identify or cannot resolve some details which are very much short to it. That means whenever we are seeing an object very much close to us, very much close to our eyes, we cannot identify that properly. Whenever there is some distance between our eyes and our things, we can easily identify. That in the same sense, the radar cannot identify the objects which are very, very closer to it. And another limitation is radar can recognize the color of the target. That means it can identify whether there exists a target or not, but it cannot recognize the color of the target, and also it cannot identify the internal aspects of the target. So what are present in the object cannot be identified. Okay, so that means it shows that there exists a target. That's it. But it cannot find or it cannot show that what is the shape of the target, and it cannot retrieve the target shape, and it cannot show the color of the target, and it cannot show the internal aspects of that target. So see here the principles of operation. See, whenever here we are transmitting a signal, that means from the from the transmitter section we are transmitting a signal, that is transmitting energy. the time we are sending the signal to the target, that means see, whenever we are transmitting a signal, it has to hit the target and it has to reflect back. That is nothing but a total time period. That means the time taken by the signal to hit the target and receive back to the radar station is called a total time. Okay, so the reflection of electromagnetic waves and measurement of running time of transmitted pulse. Ultimately we are going to calculate what is the transmitted power and what is the back scattered power, that means the reflected power. So based on this time, we are going to call it as a round trip time. We are going to call it as a round trip time. And what is the radar basic principles? What are the transmitting path and transmitter, what are the blocks present in the transmitter and what are the blocks present in the receiver? See here, in the transmitting path we have a transmitter, duplexer as well as receiver. In the radar station we have transmitter, duplexer, receiver, and we are going to find these received signal in a display. That means here we need to transmit the signal through a continuous transmitter. That means the wave should be in a continuous manner. So here the term called duplexer is a device which acts as both transmitter as well as receiver. These type of radars are old radars. That means there will be a single duplexer which is used for both transmitter as well as receiver. That means it will work on a time sharing basis. That means whenever the transmitter is on, then the receiver will be in off position. Whenever the receiver will be on, then the transmitter is in off position. Okay, and the display here we are going to find out the display like just a blip means a movie blinking light like that. Okay, so see here, principle of working of a radar. Transmitter will be sending a signal through antenna through air and transmitting atmosphere, and that signal will be hit by the target and the signal will be returned back to the receiver through a duplexer. So the time by which the signal is been transmitted and received back is called as a round trip time. So we need to find the range of the target. So principle of measurement is, what is the distance? We are going to find it the distance determination. That means what is the distance and where the target is been located. We are going to find that distance, and direction, it is whether it is moving towards the radar or away from the radar. We are going to find that one, and we are also finding the elevation angle along with the range resolution. So what is the basic range? That means here C is velocity of light, and delta T is the total time elapsed for two-way trip. Two-way trip means for both transmitting as well as receiving. So range can be calculated by velocity of light into delta T by 2. So see here, we have they have taken a time of 16.5 microseconds for transmitting and 16.5 microseconds for receiving. Therefore, in order to find the range, what is the range, how many kilometers it was there, they have calculated that C into, that means 3 into 10 to the power of 8 into 33 into 10 to the power of minus 6. That means this is a complete one, 16.5 plus 16.5, 33 into 10 to the power of minus 6 seconds by 2. That will be equals to 9,900 meters, which will be equals to 4.95 kilometers. Therefore, the complete distance is 4.95 kilometers. That means the target is at a range of 4.95 kilometers. So how we are going to measure this range? The most common radar waveform is a train of narrow rectangular shaped pulses modulating a sine wave carrier. That means we are transmitting a rectangular pulses, it's a narrow band of rectangular pulses which are used as an transmitting signals. The distance or range to the target is determined by measuring the time taken by the pulse to travel to the target and return back. That means TR, this is also called as round trip time. So we are going to find the distance or range will be calculated by the measuring of the round trip time. That means that is the time taken by the radar or the signal to return back to travel from the radar station to the target and return back from the target to the radar station. Since the electromagnetic energy propagates at the speed of we are seeing that light of the speed of the light, as I have already told you in this example. C is nothing but velocity of light, that is 3 into 10 to the power of 8 meters per second. So the range R is given by C into TR by 2. That means TR is nothing but here delta T. So the two factors appear in the denominator because the factor 2 appears in the denominator because of the two-way propagation. As I have told you that transmitter here transmitting and receiving. Here two instances both for transmitting and receiving. We are taking the average. So the range R in kilometers or nautical miles. That means whenever we are working in aeroplanes or aircraft systems, we are going to calculate or the speed of an aeroplane will be in nautical miles, and 1 nautical mile equals to 1.15078 miles or 1.8412 kilometers. Okay, and 1 mile equals to 0.8689 nautical miles or 1.6 kilometers. Okay, and this results in an incorrect or ambiguous measurement of the range. So that means here by taking these values we are not going to find out the value exactly, because as it is in what we call first radar, that means initial radar, we are not going to identify or we are not going to get the value at a proper manner. Echoes arrived after the transmission of the next pulse is called a second around time echo pulses. That means whenever the signal which we have received after the second pulse, those are called as second time around echoes, and such an echo would appear to be at a closer range than the actual. That means whenever we are sending the signal continuously without giving any time delay, if you are sending the signals continuously, it will be somewhat closer. There will be somewhat a difference between the first transmitter signal and the second transmitter signal, but it will be very, very much nearer to that one. So it will lead to misdetection, or sometimes we cannot find out, or sometimes we cannot we may be confused that which one is the first one and which one is the second one. See here, such an echo would appear to be at a closer range than the actual, and its range measurement could be misleading if it were not known to be an second time around echo. Suppose unless and until we have to make a mark that this is a second one and this is a first one, otherwise we are going to get confused. The range beyond which the target appears as second time around echo is the maximum unambiguous range. Here unambiguous in sense a clear range, ambiguous in sense unclear range. So we need to calculate the maximum unambiguous range. So the maximum unambiguous range is nothing but the maximum range, and it is the longest range at which a transmitted pulse can travel out to and back again between two consecutive transmitted pulses. That means in other words, Rmax is the maximum distance a radar energy can travel around trip time between pulses and still produce reliable information. That means we are sending the transmitting signals continuously, and we are obtaining the signals continuously. So by making the value or by making identification of this Rmax, we are going to find out, or we are going to have a clear signal or reliable information. So once a signal is radiated into space by a radar, sufficient time must be elapsed to allow the echo signal to return back to the radar before the next pulse is transmitted. As we have told you that some time difference must be there between the two consecutive pulses. If there is no time, then we are going to have an ambiguous range, that means a unclear range. Suppose if we have enough time between the two pulses, then we are going to have our unambiguous range, that means a clear range. See the next one. The rate at which the pulses may be transmitted therefore is determined by the longest range at which the targets are expected. We need to find, so that means suppose if the target is at 2 kilometers, we have to send a signal which will be there up to 3 kilometers. That means we need to extend. We cannot identify whether it will be in a proper manner or improper manner. That means we need to send the signal that should be somewhat higher than our regular signal, and if the time between pulses TP is too short, an echo signal from a long range target arrive after the transmission of the next pulse and mistakenly associated with the other pulse rather than the actual transmitted pulse earlier. That means whenever we are transmitting the next signal, if it is if the target is very much nearer, that means there will be some disturbance in our received signal, which shows that sometimes we may miss, or sometimes we may get confused that which one is the first one and which one is the next one. So we need to find out the maximum unambiguous range, that is R max, that is we can also call it as an radar range equation. So the maximum unambiguous range R max is the maximum range for which small t less than capital T. Small t is nothing but the what we call time duration. Capital T is the complete time duration. So R equals to C into, that means velocity of light into capital T minus tau, that means length of the transmitted pulse divided by 2. That means R max is nothing but unambiguous range in meters, C naught is nothing but speed of the light or velocity of light, T is the pulse repetition time, and tau is the length of the transmitted pulse. Therefore we can calculate the R max by C by 2 into FP, that means pulse repetition frequency. Pulse repetition frequency, that means what transmitter length of the, if the transmitter length is short, tau can be ignored. See, if here we have in the previous one we have C into T minus tau by 2, that means here we are neglecting the tau if the transmitting pulse is very less. Okay, so 1 by tau is nothing but pulse repetition frequency. So the very important thing is, and frequently asked question is, we need to find out the simple form of a radar equation. So in order to find the simple form of radar equation, that means we are going to calculate the R max, that means the unambiguous range. So it relates the range of a radar to the characteristics of the transmitter, receiver, antenna, target and the environment. This simple radar equation relates all these type of blocks, that is a transmitter section, receiver section, and the type of antennas what we are using, and the type of targets what we are going to identify, and also the signals what we need, or what type of signals we need to be sent based on the environmental condition. Useful as a means for determining the maximum measurable distance from the target to the radar. That means it is very much useful to find out the maximum measurable distance. That means we should not take an accurate what we call an inappropriate range. We should be take an appropriate range to find the distance. It serves both as a tool for understanding radar operation and as a basic for radar design. We should find the radar distance as well as a basic radar design. We should find the tools. Okay, and see here the power density from isotropic antenna, the type of antenna what we are going to use, PT is equals to PT by 4 pi r square. Initially we need to transmit a signal Okay, so some of the parameters like we need to find or we need to take into consideration are, we should take an antenna which is producing higher gain, and we should at both ends, that means transmitting as well as receiver section, and peak value of the we need to find the peak value of the transmitted power, and receiver power received power of the receiving antenna, and area of cross section of the target, and effective area of the receiving antenna, and distance of the target. Initially we are going to find the targets, or we are going to use omnidirectional antennas. That means the signal will be radiated in all directions. Okay, in all direction uniformly. That means we are unable to find, sometimes we are unable to find the targets if there is no or we are going to waste those things. So in order to avoid the loss of signals, we are going to use directional antennas, so which shows that the total completed signal will be transmitted in one particular direction, so that the gain should be high. For that, the power density of the from a directive antenna PE or isotropic antenna PTE, P equals to PT by 4 pi R square. Okay, and power density from the directive antenna is nothing but PTG by 4 pi R square, where G, or we can call it as an GT. Okay, and the power density of echo signal, received echo signal, is given by PT GT by 4 pi R square. Okay, and if the power of the radar transmitted is denoted by PT, and if an isotropic antenna used, that means one which radiates uniformly in all direction. As I have already told you that we are going to use omnidirectional antenna. Okay, then it will be equals to P equals to, see here, P equals to, see here, isotropic antenna power density equals to P equals to PT by 4 pi R square. So we are taking we have to find, or we have to use an antenna which having highest gain. That's why power density of the directive antenna will be equals to PTG by 4 pi R square. So coming to the next one, as we have we need to determine the cross section of the target also. So therefore we need to find the ability of the target to reflect energy is dependent upon the cross section of the target. So then we can determine the power value as here PR, received power, is equals to PT P suffix T G or a GT into sigma, which is nothing but area of cross section, that is into divided by 4 pi R square. 4 pi R square. That means we need to find the ability of the target. That means that will depend upon the area of cross section, and the power density of the receiver antenna. So power density of the receiver antenna will be calculated by PR, or P complement. Wait a minute. That means we can calculate P complement. Okay, P complement equals to P by, capital P by 4 pi R square. 4 pi R square. So we need to substitute this value here. That means P in sense PR, P in sense PR. That means therefore PR equals to, we need to find that. Then P complement will, what is the value of P complement here? Therefore P complement equals to PR. That means PT GT sigma by 4 pi R square whole square. Okay, so and the received power, so received power at the antenna is given by PR is equals to PR is equals to, this is P only, not PR, pardon, this is P only, I will erase that one, this is P only. Okay, now received power PR is equals to P complement into AE, that is AE is nothing but effective area, so that means substitute the value of P complement here, then PR equals to I will take another slide, so I will write here, so PR equals to PR, I will take another color, I think it's not visible for you, erase this one also. Okay, so PR, received power PR is equals to PT power of the transmitting antenna, GT gain of the transmitting antenna, sigma area of cross section by 4 pi r square whole square into AE, that will be equals to PT GT sigma AE by 4 pi whole square into r power 4. Can write like this, PT GT sigma AE by 4 pi whole square into r power 4. That means why I am bifurcating means we need to calculate this range. So PR equals to PT GT sigma AE by 4 pi whole square into r power 4. So we need to calculate the range. So r power 4 equals to PT GT sigma AE by 4 pi whole square into PR. So whenever we need to assume that whenever received power is minimum, whenever when PR equals to P min, that means minimum value, then R equals to R max, that means maximum range. Therefore we need to calculate this R max. R max equals to R max, that means maximum range equals to PT GT sigma AE by 4 pi whole square into P min whole to the power of 1 by 4. Okay, this is a simple form of radar equation, and the relationship between the area and effective area of the antenna. So we need to this is a simple form of radar equation, and the modified equation is, that means they are relating with another thing. So for example, I'll explain here itself. See, so the relationship between the normal area and the effective area of an antenna. So here we have taken area, effective area is given by capital A, normal area and effective area is given by rho into AE, rho A into AE. So this rho A value will be equals to 1 for omnidirectional antenna and 0 for another antenna. That means we need to find what type of antenna we are going to use will be determined here. So according to antenna theory, the relationship between antenna gain and the effective area of the receiving antenna is given by GT. That means this antenna gain with respect to effective area of the antenna is given by GT equals to 4 pi AE by lambda square, 4 pi AE by lambda square, where lambda is the wavelength. So we need to find out this AE, effective area. AE equals to AE. Instead of AE, we need to substitute these values. That means AE equals to GT lambda square by 4 pi. GT lambda square by 4 pi. So substitute, let it be equation 2 and let it be equation 1. R max equals to, this is equation 1. Let it be this one. Okay, substitute the value of AE that equals to GT lambda square by 4 pi here. So then R max equals to the final result or a modified value. Then R max equals to instead of AE, you need to substitute that one. That means PT GT square. I am writing because instead of AE I have substituted GT lambda square, PT GT square sigma lambda square by 4 pi whole cube, into P min, P of minimum, P of min, P min whole to the power of 1 by 4. This is our modified radar equation. So by taking this equation, we are going to find out the maximum range of a radar signal. So in the next class, we are going to discuss about the frequency ranges or a block diagram of radar and some of the things. Okay, thank you.